We're going to look here at the idea of differential equations and solving differential equations. Now, differential equations are a topic in mathematics that actually spreads a broad area. And there are actually just even branches of study of different types of differential equations. In this video, we're going to just scratch the very surface of the idea to see a process where we will utilize our basic indefinite integrals that we have been working on. Now, I've put all the rules for the indefinite integrals that we've been working on so far, and I've got a couple of differential equation examples to do. A differential equation by definition is an equation in variables and their derivatives, and which then when you find a solution of the differential equation, you're looking for that function so that if you took the appropriate derivatives of that function and you plugged in the function expression and the derivative expression, you would get a true statement. So I'm looking for an equation as an answer to a differential equation. Now, if I don't have any specifics about the solution that I'm finding, then I get a general solution and I'll have a plus c term in my solution. If I actually have extra information about an ordered pair that my function goes through, I can actually find the value of that constant term and give a particular solution. Let's look at these examples. So the very first one is f prime of x is equal to 6x squared plus 5 is my differential equation. And then I have this information that f of negative 2 is equal to 10. So that function answer that I'm looking for, if I put negative 2 through for the x's, I'll get 10 out for the y. Now we're going to start by working with the differential equation and trying to find the general solution. So we have our f prime of x is equal to 6x squared plus 5. And the very beginning, to help us get started with things, we want to change out of the derivative notation they're currently using into the notation dy dx. So if f prime of x, you're going to write the dy dx. If they start with y prime, we'll write the dy dx. Just to get that notation introduced. And next what we're going to do is we're going to now write it as the differential of the dependent variable is equal to the derivative times the differential of the independent variable. So we are going to write dy is equal to our 6x squared plus 5 dx. And that gets us set up. Now what we want to do is go ahead and integrate. And we want to recognize again that I have all the x's and the dx on one side and the dependent variable dy on differential on the other side. So when we integrate both sides, well, the integral dy, we'll think the integral dy, that's just like if I had the situation of the integral dx. It's just there, it's with the variable y, here it's with the variable x. Well, that integral is the same as the integral of 1 dx, which goes and integrates back to x plus c. Now we're going to put all our plus c's on the right-hand side, but what I wanted to take from that is that the integral of 1 dy is y. And then that's equal to. Now here it's an integral of two different terms in my integrand, and I don't have an exponent on the parentheses, so I don't have anything to multiply out. And if I have multiple terms that I'm integrating that is in that integrand, then I can do term by term integration. So I have the integral of f of x plus or minus g of x dx is the integral of f of x dx plus or minus the integral of g of x dx. So I'm going to do that next, as well as I can pull out number factors. So we are going to write this as 6 times the integral of x squared dx plus 5 times the integral of 1 dx. I factored out the common factors, and we can do that with indefinite integrals. Now we are going to apply our rules. So the integral of x squared dx, you add 1 to the exponent and divide by that. That's letter-based to number power, where my number power is not negative 1. So I have our base of x, add 1 to 2, you get 3. And when I have my 6, I'm going to multiply that to dividing by 3 is like multiplying by 1/3. Then plus 5 times the integral of 1 dx is x, and then plus c. So now I have y is equal to, well, 6 times 1/3 is 2. So I have 2x cubed plus 5x plus c. That is my general solution. Now to find my particular solution, this is the point in time that you take out the x's in your function, put in -2, and then take out the y and put in 10. So 10 is equal to 2 times -2 cubed plus 5 times -2 plus c. Remember, order of operations, that's -8 times 2 is -16. So I have 10 is equal to -16 minus 10 plus c. And when I combine those like terms on the right, that'll be -26 plus c. So we will add 26 to both sides and get 36 is equal to c. And so my final particular solution to this differential equation is I'm going to write my general solution, except we're going to replace the c with 36. So I have y is equal to 2x cubed plus 5x plus 36. Now let's look at the next one. Here I have my differential equation f prime of x is equal to sine x plus 1, and I have if 0 goes in for the x's, the value that comes out for y is 3. Again, instead of f prime of x notation, we are going to write dy dx is equal to sine x plus 1. Write it into the differential notation, dy is equal to sine x plus 1 dx. Integrate both sides. The integral dy is y equals, the integral of sine x is negative cosine x, plus the integral of 1 dx is plus x, and then plus c. Now again, that's your general solution. Our particular solution, we need to find the c and then write that in the placement of the term here. So we are going to put 3 in for the y is equal to negative cosine of 0 went in for x plus 0 plus c. And remember, the cosine of 0 is 1. So we have 3 is equal to -1 plus c. Add 1 to both sides, c is equal to 4. And now write our particular solution, that y is equal to negative cosine x plus 4. Well, I hope these 2 examples of differential equations help you get a little bit of a start into working with finding solutions of very, very basic differential equations, and also more practice into finding the values of your indefinite integral.